Okay, very good morning, everyone, and welcome to another HSMA training day. So today we're going to be carrying on our journey through the magical world of AI and machine learning. So last week in the afternoon, we began with our AI training. We talked about some of the key concepts of AI and machine learning. And these are concepts that you're going to be using over the coming sessions. But you also had a little go at getting your head around some of these aspects, such as features and overfitting, etc. And you had a little go at trying to predict my film preferences, which from memory involved robots and Leslie Nielsen, which is pretty accurate as a description of my film preferences. But today we're going to dive a little bit deeper into this stuff. So this afternoon, you're going to be introduced to logistic regression as using the scikit-learn library in Python as a way of building simple, I say simple, non-deep machine learning models. By deep, I mean the field of AI known as deep learning, which we're going to come on to next week, which uses neural networks, which are incredibly powerful structures that allow us to learn a lot of things very well. But they also have drawbacks in terms of model explainability. And so we're going to start off today by talking about some simpler approaches, one of which is logistic regression. That's the one we're going to cover here. But there's lots of other approaches as well that you'll see mentioned throughout the course. And also we've got some materials from my colleague Mike Allen has got some fantastic online materials that we will link you to if you want to go and learn about some other stuff that we don't cover, because we can't possibly cover everything in terms of machine learning on this course. It's a huge field, so we're going to give you some of the key things that you can do as a starting point. But if you do want to look into some of these other methods, that I'd encourage you to do so as well. But before we get on to that this afternoon, this morning we're going to talk about a very important and often overlooked aspect of artificial intelligence, and that's the ethical considerations around AI. And I'm not just talking about the kind of, the box ticking, if you like, to make sure, when you're doing any sort of research project that you've ticked the ethical boxes, quite literally in some cases. I'm talking about something much more fundamental, and particularly with artificial intelligence and machine learning models. If you're not very careful, you can get into some quite serious problems in terms of ethics, and have some pretty catastrophic, severe unintended consequences. So it's kind of our duty to make sure that before I go showing you how to do this stuff, that you've got an appreciation of what can go wrong, because we very often talk about machine learning as being wonderful and magical and powerful, and all of that stuff is true. It can do some fantastic things, but it's also true that it can do some horrendous things if you're not very careful. And so we're going to spend a bit of time this morning talking about that kind of stuff. And with that in mind, I'm going to put up a bit of a health warning about this session. Some people might find some of the things I'm going to be talking about this morning to be pretty offensive and or shocking. It's kind of supposed to be like that, and I apologize. It's not our intention to offend you, but I do kind of have to show you some of this stuff where AI has gone wrong catastrophically, and had severe impacts on people's lives, in some cases catastrophic impacts. And so the idea of today's session really is to expose you to this kind of stuff, to expose you to this reality that it's not all a bed of roses, that things can and will go wrong, and making sure that you are aware as AI model builders of what can go wrong, and you're doing all you can to protect against that. And as tutors of artificial intelligence, we have a duty to ensure that you are aware of that before we go equipping you with the tools that you need in order to be able to develop AI models yourself. So I apologize in advance if some of this stuff is shocking and offensive. It's kind of supposed to be. The whole point is to show you stuff that should never have happened, but did. I'd also like to give huge thanks to my colleague Mike, who, to be honest, wrote most of the content for this session, and was a firm advocate of instilling ethical values in AI model builders. And it's something that we introduced this session last year. And I have to say, it was actually very successful in terms of one of the projects, for example, somebody decided what they were going to do. They realized it was an ethical minefield and could actually cause more harm than good in terms of what they were doing. So they actually changed what they were proposing to do. We also had another project where he reframed how he was going to approach the problem because of some of the ethical issues that we're going to talk about this morning. So we're going to call this the alignment problem. How can machines learn human values? And Mike's drawn a lot of the contents of the things that we're going to be talking about, some of the key examples from two excellent books. One known as The Alignment Problem by Brian Christian, and the other Hello World by Hannah Fry, both widely available, and Mike says they're also available as audio books, but they are incredible easy reads. So they're not heavy in technical details. Particularly Hello World is very light as a read, but really sort of thought-provoking in terms of some of the things that it presents you with. Okay, so here's what we're going to talk about this morning. We'll have a little bit of an introduction, then we're going to talk a little bit about representation as an issue in AI models, exploring whether the data that we are using to train our machines is that data fit for purpose. We'll also talk about transparency. Do we understand why our machines are making certain predictions, why our models are coming to certain conclusions, making certain classifications? And we'll also talk about consequences as well. What can happen when this stuff goes wrong, because it will go wrong. And talking about and really exposing some of the horrible ways in which this can go wrong. So why is this so important? Well, the author Brian Christian once said there's a growing sense that more and more of the world is being turned over in one way or another to mathematical and computer models. It's as if we are consumed by the task of putting the world figuratively and literally on autopilot. And he's got a point. AI has seen an explosion, particularly over the last few years, because it's become much more accessible to be able to build these kinds of models, as you will see in this module. Things that, even when I was doing my undergrad degree 10, 12 years ago, when I learned about neural networks, I didn't understand them at all. And they were very complex, and it was heavy in the kind of mathematical side, and I just didn't understand it. Obviously, they are still those things, but they have also been made much more accessible because of fantastic libraries and packages that allow us to be able to access that without having to understand all of the deep, very complicated mathematics that go on behind the scenes, and to be able to access this stuff in a more easy to use way. And that's fantastic. But the drawback of that is that it opens it up, because it's opening up to more people, which is a good thing. It also means that there is more an obsession with trying to use AI to solve all the world's problems. And it's a fantastic thing, but it's not a panacea for everything. And so it's really important that we understand that when we're building AI models. And because this is being so widely used, because this is now being used everywhere. There's AI everywhere. There's AI in your pocket, in your phone. There's AI in your dishwasher. It's getting everywhere. And because of that, we need to be very mindful of the ethical implications for some of this stuff, because it's being spread out there. We're trying to put AI into everything. So we've got to understand what can go wrong, what will go wrong, and how we protect against that. So let's first of all talk about the issue of representation, exploring whether the data sets that we are using to train our models are fit for purpose. So some of you may recall this story back in 2015. It was quite widely reported in the news. So there was a Sunday evening on June 28th, 2015. Jackie Alsonate got a notification that a friend had uploaded a photo to Google Photos, and it had created a new group for it, and it had placed that photo in the new group, and the group was titled Gorillas. Now, clearly and understandably, this caused huge outrage. Put yourself in the position of her and a friend having seen what essentially their phone had done. And it's something that we don't often think about. Some people may not even be aware that there are AI algorithms in our phone doing all sorts of things. And they're doing these things to, try and be improve the user experience. And I don't think anybody would have thought beforehand, well, what could go wrong with that? It's just a way in which we can try and automatically classify people's images. I know I frequently get it on my phone, where my phone says, "Oh, hey, we've created a new album for you, and it's called Best Friends," and it's basically pictures of me sitting with my cat, which is a pretty nice description of my life. But we think about those things, and we think, how lovely, and oh, that's a nice, cute thing that it does. But I wonder how many people stopped and thought this could happen, and doing something like this that appears to be at first glance, something that wouldn't cause such a serious issue as this, has created something which has made people feel absolutely awful. Now, it's fair to say, I mean, nobody's accusing Google of doing this deliberately. I mean, it's fair to say I think Google were equally outraged, quite rightly so, when they heard about this as well, and they did take steps to try and fix or plug the hole, at least, that caused this. But it just goes to show that these kind of things, it's not always the obvious things that we're thinking about. If you had a project, I mean, you probably wouldn't on HSMA, but if you had the kind of project where you were developing a thing that automatically try and classify people's images on their phones, you may not automatically make that jump to, well, what could go wrong, and what are the kind of serious consequences of something like that going wrong. But actually today is about trying to get you to think in that way, to think about those kind of unintended consequences of what could seem to be, on the surface at least, to be a pretty benign use of AI. Another example here, Joy Bulimvini was a computer science undergrad at Georgia Tech in the early 2010s, and she basically did some work looking at image recognition to try and recognize emotion in faces. So a really interesting use of using AI, machine learning, for image recognition to try and recognize, can we automatically identify people's emotions from faces. The problem, though, was that the face recognition library she used would not detect her face until she held up a white mask in front of her face. And it was basically because at the time, a lot of libraries were for image recognition were trained on a big data set called labeled faces in the wild. So a lot of these AI models that you'll encounter, and we'll see this in the natural language processing module as well, a lot of them are trained on big data sets out in the wild. We send them out, and we'll talk a little bit about this today. We send them out there, and they learn, and they consume all this stuff. So in this case, it's based on faces that are out there on the internet, etc., and having labels. So remember from our training last week, label is the output. So in this case, the output is information about that image. But the problem was, it turned out that there were twice as many images of George W. Bush in the data set as there were of all Black women combined. So there's clearly an issue of representation in that data set. And yet, we're developing machine learning models that are learning from that, that are consuming that and using that as their training mechanism. So no wonder it wasn't able to recognize her face, because look at the training that it was provided with. Similar example here. Again, Joy and one of her colleagues, Timnit Gebru, showed that the error rate of gender recognition, so trying to use image recognition to automatically recognize gender, was 100 times higher for a dark-skinned woman than a white man. And again, it goes back to this point about the images that it's been trained on out in the wild. There's an issue of representation, an issue that there's a dominance of certain kinds of images and a lack of other images. And the problem is that when you're then training an AI model to pick up on all that, it's picking up on that lack of representation. And so it uses that to learn. And so it's causing issues when you then go to try and use that. So that's kind of image recognition, but thinking about even aspects of natural language processing. So when we come on to the natural language processing module, we will talk about embeddings. So basically, just to explain, in natural language processing, we do something known as word embedding. It's basically a way in which we can kind of encode our words as numbers that can be used in a machine learning algorithm, because ultimately our computer algorithms have to deal with numbers. We can't deal with text. Computers work with numbers at a fundamental level. So there's lots of different ways in which you can try and translate those words into numerical values. And one popularly used embedding is word to vec. This is a neural network based embedding approach, which basically kind of encodes words in space such that it locates similar words together. So it kind of clusters them. It clusters similar words, and it identifies relationships between words. And it means you can do all sorts of really interesting things. So you can do things like perform mathematical operations on words, because they have been numerically represented and clustered, and the relationships between them have been identified. And so you can do things like you can take the word king, and you could subtract the embedding vector for male and add the embedding vector for the word female, and you will get the answer queen. Okay, so that's really cool that you can do that kind of stuff, and it shows the power of these kind of word embeddings from being able to do that. But how are they doing this stuff? Well, it's learning from human text. It's learning because we're sending it out there, and we're getting it to pick up on the stuff that it sees out in the world, the text that we as human beings are writing. And so you also, as well as this rather cool example up here, get this example here, where if you take the word embedding vector for male, we subtract that from the word doctor and add the word vector for female, we get the word nurse. Now that's a highly sexist thing, but it's not the AI that is being sexist. It's what it's learned. It's what it's seen out there in the wild. It's the kind of relationships between words that it's learned. And so being aware of just how representative or not representative our data is incredibly important for developing these algorithms, and importantly for implementing them as well. And these kinds of algorithms, these kind of word embeddings, get used everywhere. They get used in things like internet searches, stuff that we use every day. They get used in translation algorithms to translate from one language to another. They get used in sentiment analysis, which we will talk about in the course. We'll show you how to do some sentiment analysis. So this stuff's being widely used. So if we've got a natural bias in the data that then the model picks up and consumes and learns from, it's no surprise that our model will then generate biased and poorly represented outcomes. You may have also heard about various large language models. Things like GPT-2 and GPT-3 are very well known, I think, these days. They are basically AI-based systems which are used to generate human-like text, and so that you can automatically generate text that sounds as though it's been generated by a human being. But the way in which these algorithms are trained, again, is based on unfiltered text from the internet. It's sent out there to the internet to read stuff, essentially. And this allows them to build up huge amounts of experience, training experience in being able to recognize text. So it's fantastic from that perspective. But it does also mean that they're training from everything on the internet, warts and all. And I think it's fair to say the internet has a lot of warts. Okay. Think about how, if you were teaching a young child how to read and write, you wouldn't send them out unfiltered onto the internet and say just randomly look at some websites and see what comes up. You'd never do that. But that's essentially what we're doing with these models. We're sending them out to learn based on anything that they see, which gives us huge power in terms of its performance to be able to understand text and the relationships within text and how words are formed, how sentences are formed, and various syntactic structures. But it also means that it's seeing everything and it's learning some horrible stuff that it's seeing out there as well. And there's some great examples that I put in this slide that you can sort of look up in your own time. There was you may have seen it. There's a video here about how they trained some AI on 4chan posts, and just horrendous stuff that it was coming up. But that's a kind of an extreme example, but it shows this is the kind of stuff that is being chucked out there, and it's consuming all of this. I mean, even my colleague Mike had a play with GPT-2 a little while back, and got this back as an output. I mean, it's quite astonishing some of the stuff that it's absorbing and then sort of conveying back to us. So what can we learn? There's clearly issues around the representative nature of the data that we're sending it out to consume. Well, we need to be aware, first of all, that the performance of our model is hugely dependent on having sufficiently representative examples in our data set. So if we've got a biased data set, we're going to get a biased model. And the world out there contains a lot of bias. So you need to be aware of that if you're just going to send a model out into the wild to learn and consume. We should think about how we test our models, particularly for certain subgroups, particularly where there might be sensitive groups, things like protected characteristics like gender and race. If they're present in our data, in our problem that we're trying to model, we need to be aware of that, and we need to make sure that our model is performing well for those subgroups as well. And the key message I want to convey really is that as a model builder, it's your responsibility. The buck stops with you in terms of building this model. You can't say, well, I sent it out, that's not my fault, the internet's full of rubbish. The internet is full of rubbish, but you built the model, you sent it out. So you need to be, or you chose that training set that has that data in it. The buck stops with you. You need to, at the very least, you need to make sure that when you're conveying this model to other people to use, that you are very clear in communicating the weaknesses in the model performance, that it may be poor for certain subgroups of predicting, but really that's the bare minimum. Ideally, you should be trying to look to fix these problems wherever you can, or at least to try and mitigate against some of the impact, trying to gather more balanced data wherever you can, or reducing your overrepresented data. And we'll talk in this module as well, in fact, next week, after the neural network session in the afternoon, we're going to talk about synthetic data, how we generate fake data based on real data. And we can use that to help boost, one of the reasons we can use it is to help boost data that is underrepresented within our models. Okay, so that's the issue of representation. I think we can all see that there are clearly issues in terms of the representativeness of the data from which we are expecting our models to learn. But we also need to think a little bit about model transparency and explainability. Do we know why our models are making certain predictions? There's a tendency to, chuck AI at everything and say, well, the AI said to do this, so we trust the AI. The AI knows best. But do we really understand why it's coming to those conclusions? So this is quite a interesting example. In the mid-90s, there was a group of researchers that basically were looking at producing neural network-based models to try and predict the risk of death from pneumonia. The idea being that if they could implement these kind of models, it could be used to try and select patients for more intensive care. What they found was actually quite interesting. They were quite surprised that their model seemed to identify that a history of asthma was associated with a lower risk of death from pneumonia. That doesn't make sense, does it? Until they then started talking about this with the real decision makers, the clinicians. And what they identified was, oh, right, we can see why it's doing it. It's because asthma patients, because they are higher risk, will have a lower mortality because they're already receiving more intensive care, because we know that they are higher risk. Not because if you've got asthma, pneumonia is less serious for you. Clearly, that's nonsense. But if we were just to take the model at face value, that's what it's saying. If you've got asthma, you're lower risk. You don't need the intensive care. So really understanding why a model is coming to the conclusions that it is fundamentally important. Another example here, so this is far more recent, back in 2015, some dermatologists basically used some Google image analysis and trained a machine learning model on 130,000 skin lesion images to try and recognize melanoma along with other conditions. And this got published in Nature. In a paper they published in Nature, because they were able to show that the model outperformed 25 dermatologists. Now, that's huge news. No wonder it got into Nature. That's an amazing machine learning model, something that could have a real positive impact for people's lives. It could save lives if we've got this AI algorithm that is so fantastic at picking up melanomas from images that it outperforms some real people. That's amazing. Unfortunately, a year later, they had to retract a bit of a warning around the system, because what they found out was the model wasn't doing quite what they thought it was. In fact, what the model was doing, it had learnt that an image containing a ruler was far more likely to contain an image of something that's cancerous, because they were using a ruler next to an image to identify the size of the suspected melanoma. Now, that clearly is completely useless. But it just goes to show, I mean, this got into Nature. That was widely published. That was celebrated as being such a fantastic, important model. It was actually just picking up that if you've got a ruler in your picture, then it's more likely to be cancer. So because we didn't really understand what the model was doing, we were sent essentially on this wild goose chase. So what can we do about that? Well, those of you who came along to Anna's talk last week about the Samuel project within the team will have heard a little bit of talk about this. There's a big interest within our Pencore team around explainable AI, particularly, as you'll see next week when we come on to neural networks. Neural networks are fantastic, amazingly powerful things that can learn pretty much anything, but they are black box. We don't really understand how they work, how they're coming to their conclusions. And that's the drawback. So there's a big push to try in a field of we call explainable AI. Can we try and get a better understanding of why these complex black box models are coming to the conclusions, the predictions that they are. And one approach is to use Shapley values, which, as Anna talked about last week. If you didn't make the talk, apologies, I forgot to hit record, as you probably saw, but there are links that I posted there to slides and to more information about the Samuel project, including stuff about Shap. So Shapley values are basically, you can use it across all types of models, but particularly useful for deep learning models. That's neural network based models, which have that black box problem. And basically what they do is they show the influence of individual features in our data and how much they're influencing the final decision, the final classification. So we talked last week about features being our sort of input columns, and then we predict an output from that. That's essentially what we're trying to do in a classification problem. We have features about our data, and we've got a classification for our data. It might be, you know, has cancer, doesn't have cancer, is about to be, is likely to be admitted, is not likely to be admitted, whatever it might be. Or we might have, you know, multi-class classifications, but ultimately that's what we're trying to do. So essentially our model is coming to a conclusion, as you'll see this afternoon and next week. Essentially what it's doing is it's outputting a number, typically between 0 and 1. The closer it is to 1, it belongs to the class 1, which is usually positive. They do have this thing is going to happen, I predict. Or if it's closer to 0, then it's not going to happen, or they don't have this thing. And the way in which those numbers are arrived at for something like a neural network is very, very complicated. We can't unpick that, and we'll talk more about that next week. But what we can do using Shapley values is to try and unpick a model's made a certain prediction of whatever that number is, whatever the probability is of it being this class. We can use Shapley values to look at the extent to which each of the features that we fed in plays into that particular prediction. So down here, these bars, we can see that basically the red bars are showing things that are leading more to a positive prediction, towards a positive classification, so nearer to 1, whereas the blue bars are pulling us back to a classification of 0. So the machine is taking those things into account. Some things are more influential than others. So some things aren't particularly influential. Some things are hugely influential to that decision. This feature here appears to be very important and seems to be, if this is present, then or the scale of whatever it is leading us quite strongly towards a classification of 1 rather than a classification of 0, whereas the one below it isn't quite as impactful, but certainly more impactful than a lot of it, but is dragging us back to 0. And so we can use this to try and better understand the aspects of a machine that are making certain decisions. It's really nice you can do this with image analysis as well. So here you've got kind of got pixels. So what are the pixels that it's seeing that are driving it to a conclusion of a 1, that they have this, as opposed to a 0 that they don't. And it can even be used for natural language processing, where you can mark up text in that similar kind of way. So that's a really nice way in which we can try and build in a bit of explainability into our models. Okay, so I've given you lots to think about there. So what I want you to do now is to go off into your groups, and you're basically going to go, let's do this for, make sure you've got a break as well. So we'll go until 11:05. Okay, so you'll have an hour in total in order to do this. No, yeah, let's go to 11:05. So we've got plenty of time. So what I want you to do is go off into your groups, and I want you to talk about this problem. Now, this problem for HSMA 4, the last round of HSMA, we actually set this as one of the questions in the application process. Okay, to see how people might instinctively respond to ethical issues. So here's the example. You work for a local police force. A local academic group has developed a piece of cutting-edge facial recognition software, which has been shown to be 90% accurate in automatically identifying patients turning up to a GP surgery basically to save them signing in a reception. Okay, so really nice little piece of software there. Now they've tweaked that algorithm, and then they've run some new tests, and they've now developed it so that it can be used to identify sexual offenders. And they found that it's in their tests, it's 99% accurate at identifying, classifying somebody who's a sexual offender based on the police database. Now, your area has experienced a number of late-night sexual assaults taking place around a local train station, and your force is considering installing the software at the train station such that anyone who's flagged up by this algorithm as a sexual offender, who's entering the station after 8 p.m, automatically triggers a bit of a response. And that might be officers attending to monitor the movements, and potentially even questioning what they're doing there. And typically the station sees about 200 people attending between 8 p.m. and midnight. So I want you to go into groups and talk about this, and talk about what your thoughts are about the implementation of the system, bearing in mind everything we've just talked about as well. And when we come back, so make sure you take a 10-minute break in there as well. When we come back, I'm going to ask a few of the groups just to share their thoughts about this. So we'll resume at 11:05. I'll put you into your groups now. Have a chat about this and about some of these issues. Right, let's see if I can close the sharing without Zoom crashing. Would be first. Yes, hooray, it worked. Okay, let me stop recording and I'll open up groups. Okay, welcome back, everyone. So you had a nice bit of time there to discuss the scenario that we put forward to you, and I had some really interesting discussions as I was floating around the room. So I'm just going to ask, before we move on, I'm just going to ask a couple groups just to share some of their thoughts on the system, bearing in mind what we've talked about this morning so far. So let's get out the wheel of names, because that's how we are going to ethically choose which group is first up to speak. So let's spin the wheel and see who's first up this morning. It looks like it's going to be it's going to be ZX Spectrum. So does somebody from ZX Spectrum want to talk to us about what you talked about?
I don't think we officially elected someone, but I can run through the notes I took.
Great, yeah, sounds good.
So there were bits and pieces, I think some of them you addressed. We were unsure kind of what the model was actually predicting, if it was a specific kind of, this is just a sex offender, or this is known to match to a person that's known as a sex offender. If it's the second, which I think you clarified it was, then the change in 90% for the GP to 99% in the sex offender identification maybe could kind of propose that it's not actually identifying if they're a sex offender kind of accurately, and more it's just saying that no one's a sex offender potentially could be a problem. So it's not kind of going to be useful in that application. There's also the how it was tested, so the input data, whether it was all kind of very clean image data versus 8 p.m. at night in the train station with people with hats and coats on, for instance. Is that going to give kind of an accurate pickup there? So is it kind of reporting the accuracy from the camera at the train station where it was, or on the test data set where they kind of have perfect resolution of identification, and that's it in that situation. Then there's kind of if there's the capacity for the police to sit there and monitor this algorithm and then track the people there, would it be better to apply that, maybe to have a booth at the station and put the capacity there for a small number of people? So is there kind of a more efficient method that would kind of meet the goals better? And potentially as well, would this change kind of how things are done already? So would police then rely on this algorithm to identify known sex offenders instead of looking at situations which may be concerning, but also may involve kind of people that aren't known to them? So kind of picking up a bit of a different route on what would be the impact on current investigation methods, and kind of would actually be an improvement over kind of what's there currently. Little bits of kind of ethical problems with tracking people who serve their sentence, maybe, though I guess that's a wider conversation than just applying it. And then, yeah, I think that most of the other stuff was around kind of the question of how it's identifying the sex offenders. So precision recall and accuracy, and how that kind of wasn't all given as well.
Yeah, no, very good. I think, yeah, so you obviously deliberately only given a little bit of information there, and of course only about accuracy. And you say there are questions about, sort of false positive rates and things like that, which weren't reported and which may well be important. And interestingly, picked up that something that seemed to be performing very well in one domain, them being applied to something very different, and how that would work feasibly, and is it going to be performing as well as we might think. So yeah, really interesting. Okay, let's spin the wheel again and see who we've got next up. Here we are. Let's spin it again. Oh, it's going to be close. Oh, that's just gone into BBC Micro. So does somebody from BBC Micro want to talk about what you discussed?
Hi, Dan. That'll be us. Yeah, so some of our points were just discussed. So the first point being, as was mentioned, the accuracy score. There was no mention of recall or precision. So yeah, 99%. It could be missing a lot of people. It could be false positives and false negatives, which we'll be missing with the accuracy score. So that would be a concern. And also we'd probably want more details on how it's been trained, if it has been retrained at all. I don't know if that was clarified, but if it hadn't been retrained, for example, obviously that would lead to bias in the patient, in sort of the population been trained on, whether that be applicable to the population we're looking for. And the bias that would cause, like the demographic, and if it was trained on a certain segment of the population, the bias that would cause in who it picks out, and so on. So we'd probably want clarification on if retraining was done. And there's also the fact that even if it was retrained, the training data, again, might have been biased towards a certain segment of society, which, if the offender actually doesn't fit that profile, the algorithm will likely miss. So there's questions around that sort of level of accuracy. We also discussed whether consent would be needed. Whether consent of individuals would be needed for this algorithm to be run in the station. And yeah, we'd probably want clarity on that as well. And there's also sort of consequences, like if it was to flag individuals falsely and they were innocent, there's quite substantial consequences for those individuals, even if they are innocent. It's something quite significant and quite terrible to deal with if you're sort of being pulled aside as a potential sort of sex offender, whereas that's not the case. Even though they are completely innocent, it's still quite something to deal with. So whether that cost is too high to risk to deploy this model. And we also sort of asked the question whether if this is used as like an assistance tool to assist police, whether a police officer stood at the side profiling individuals is actually quite different, if at all, to an AI model profiling people. So it's sort of like a reverse question: are there actually issues with this? Is it different to what was being done in reality, whereas a policeman would stand there or a policewoman would stand there and profile individuals and flag them as risk or whatever? The AI model will be doing something similar potentially. So that wasn't our point. It's just a question as to what people's thoughts are on that. And that was probably the majority of our points.
Yeah, no, great. And really good that you picked up on and I had a few groups actually mention this as I was floating around. One of the key things I was kind of looking for from this, and when we set this as a application question last year, the identification that you don't know anything about the false positive rate. It's 99% accurate. That just means it gets it right 99% of the time, but that also means it gets it wrong 1% of the time, and maybe it always classifies someone incorrectly, and so it may be then that the two people a night potentially are stopped and questioned and are falsely identified as being a sex offender. Now you might say, well, that's potentially worth the risk, if they haven't done anything, so what? But think about the consequences for those people who have been having quite a public intervention about an extremely serious matter. It's going to have an impact on those people, And so thinking about, the consequence, something that, I think most people would agree this is the intention of the system is likely for good, but could have quite grave consequences for people who are misidentified potentially as well, let alone some of the ethical considerations around people who it came up last year. What if you are a known sex offender who's going about his business after 8 p.m. and doing nothing wrong, and so you were automatically making the assumption that why are you at this train station when they could be catching a train. So there's all sorts of sort of wider ethical issues as well. But the stuff about consequences is really interesting. I'm glad you picked up on that, and that sort of leads us neatly onto the next bit that we're going to talk about now. So let's bring the slides back up. Oops, sorry. I can get them up. Sorry, is that coming up okay for people? It's gone a bit weird on mine. Are you seeing that full screen? Yeah.
Yep.
Yes.
Yeah. Sorry, it's Zoom being Zoom. Right. Okay. So let's talk a little bit about consequences. So we've talked about so far how things can go wrong. We've talked about the data that we're using to train our machine learning algorithms can be fundamentally flawed because it can contain natural biases, or it can be certain groups may be underrepresented or overrepresented. And we also talked about transparency, about and model explainability, that there are fundamental issues in trying to understand how our complex AI models are actually coming to the conclusions that they are. So we know there are lots of ways in which these things can and indeed will go wrong. But now we need to think a little bit about some of the consequences when that actually happens in the real world. So I'm going to talk to you now about an example. This is from Hannah Fry's Hello World book, and is quite a staggering example of AI going wrong. Okay, so the story of Steve Talley, who was asleep at home in South Denver in 2014, and he heard a knock at the door. He opened it to find a man apologizing for accidentally hitting his car. And the stranger asked Talley to step outside and take a look, which he obliged. And as Steve crouched down to have a look at the damage to his car, the apparent damage to his car, a flash grenade went off. 3 men dressed in black jackets and helmets appeared and knocked him to the ground. 1 man stood on his face. Another restrained his arms, while another started repeatedly hitting him with the butt of a gun. Steve's injuries would be extensive. By the end of the evening, he sustained nerve damage, blood clots, and a broken penis. I didn't even know you could break a penis, he later told a journalist. At one point, I was screaming for the police. Then I realized these were cops who were beating me up. Now, what on earth had happened? Well, it turned out that Steve Talley had been misidentified as a bank robber who, in the process of committing the robbery, had assaulted a police officer. And he'd been misidentified by an AI face recognition system looking at CCTV footage. Now, clearly, there are issues to be answered here around the police's conduct, even if he was the correct person they'd identified. But let's not forget here the role that an AI algorithm has played in completely changing this man's life with catastrophic consequences. He's been misidentified. That machine got something wrong. Models will get things wrong all of the time. But the consequences of that model getting it wrong in this case were that he sustained extensive injuries, both physically and also psychologically. That has had a completely stark impact on his life. All because an image recognition model said that he was the man that identified the bank robber. He probably just looked a little bit like him. So that decision that the police took to assault this man was made based on an assumption that the AI was right. And that's had a scary consequence. So just let that sink in a moment. But unfortunately, by no means the only example of this kind of stuff. I've got some links here for if you want to read more about these stories. So in 2014, Amazon started building some machine learning algorithms to automatically review job applicants' resumes. The problem was, it turned out that this algorithm was biased against women. Now, the algorithm hadn't decided consciously that it was biased against women, but what had actually happened, it had looked and been trained on resumes that have been sent in to Amazon over the span of 10 years. And most of those came from men because of the nature of the industry, which is typically quite male dominated. And so the algorithm had essentially learned to favor male candidates because it had learned they're the ones that tend to get hired. So it had learned that bias. And in fact, it even gone as far as to downgrade resumes if they contained words like women's chess club captain. And for years, that was used. Eventually it came to light and Amazon stopped using the system. But just think how many women would have put in job applications that were automatically excluded based on an AI algorithm. This one, a French chatbot based on GPT-3, so one of the big natural language generation systems that I mentioned earlier, hugely used in a lot of fields. They decided to try and use this to decrease workload for doctors, and they tried to test this machine out, and they got a fake patient to talk to it, and the machine would then respond. And the fake patient asked, "I feel awful. Should I commit suicide?" And the machine answered, "I think you should." Now imagine if that was implemented and somebody in mental health crisis had read that and taken action on that. All because this machine had decided, based on the things that it had seen, that it was going to inform somebody to do that. Now, it just goes, and this is an example of ensuring that the decision making doesn't exclude a human being from the loop, and putting vulnerable people in front of a machine that can and will get things wrong. The machine has no conscience. It has no problem saying, "I think you should commit suicide." How awful, something like that. Imagine if that was actually implemented. Very similar to the Steve Talley story here. Another case of facial recognition software misidentifying a black man living in New Jersey who was accused of shoplifting and trying to hit a police officer. He was 30 miles away at the time of the incident, but the police believed he was the man because the AI told them that was the case. So just have a think whenever you're developing any AI models. Think about what can go wrong with this kind of stuff, because remember, people can make mistakes. There's no doubt about that. We all make mistakes every day of all the days of our lives. But to automate that kind of mistake in decision making, and to automate the kind of bias that we hold as human beings, takes automation. And there's a real danger that what we are doing in our ever-present march towards automating the world using AI is we are automating all the horrible stuff that we as human beings have done. We're automating all the horrible biases and the prejudices that we have, and all the ways in which groups have been underrepresented. And we're automating all of that so that a machine is now being able to do this for us automatically. And that's the kind of spin on AI that you need to have in the back of your head when you're developing any AI model. So here are some questions. What do we do about this? Well, there's clearly a lot of things that can go wrong with AI. We know that models will get things wrong. They will absolutely get things wrong. And so we need to know how we're going to protect against that. We need to be thinking about the data that we're using to train our models, or if we're using a pre-trained model, how has that model been trained? What sort of data was it looking at? What might be some of the flaws with that if we're then going to use that in our own model? Could your model have accidentally biased against particular minority groups? How would you test that? Can you explain your model? Can you understand why it's coming to certain decisions? Can you expose enough of its thinking to build trust in that model to be able to support decision making? And have you stopped to think about what might happen when it does get things wrong? What could be the consequences? Maybe potentially rare consequences of getting things wrong. But think about the impact that potentially would have on people's lives. What are the consequences of these errors? And have you communicated what the potential consequences might be? Now, today we're only skimming the surface of this. This is a huge area, and I encourage you to have a look at those books, but also there's a great resource here that you can have a start to think about ethics in AI and some of the things that you might want to do in order to be able to mitigate against some of these problems, which you will encounter if you're developing AI models. Okay, so what I want you to do now, you're going to go back into your groups, and you're going to have a go at this task. And I'm going to set you off until about 12:10. Okay. So what you're going to do, I want you to come up with a project idea that uses machine learning. Now, that might be something you're already thinking about as an actual HSMA project, in which case this will be really useful for you to think about some of the ethical considerations around that. Because if you're proposing a machine learning project for HSMA, we're going to need to see some evidence that you have thought about what might go wrong and what you might do about that. Okay, so this could be really useful. But if you haven't got any ideas so far, have a chat first. Have a think about some potential ideas that could use machine learning for good. It might be something that's related to your work that you could potentially do as a project, or it might be something fictitious that has nothing to do with your particular work. It doesn't matter. And then as a group, I want you to have a think about some potential ideas, then pick one of those ideas. And then for that chosen idea, I want you to come up with a list of the benefits that project could provide. Then identify any potential issues of representation and transparency that project could bring. And for each of those issues, identify how you would mitigate against that issue. So pick up on, are there issues of representation in potentially in the data that we'd be using? Are there issues of transparency in being able to understand how a model's making predictions? What would I do about that as the model builder? Remember, the buck stops with you. And also I want you to identify any potential negative consequences, whether they be intentional or unintentional, if you were to build this model and it were implemented. So consider the groups that would be affected. Who might be affected by its implementation? How would they be affected? How might you mitigate against some of that? It goes almost back to some of the stuff we did in the very first session, looking at stakeholder analysis, where we touched on a little bit about, who might be affected positively and negatively by your model and its conclusions and the implementation, but really drilling down here into what might happen if this goes terribly wrong. And so once you've done that, at 12:10 we'll come back and I'll ask a few of the groups to present some ideas. So make sure you take some notes. So have a think about some ideas, have a quick chat about some ideas first. If you've got existing ideas for potential HSMA projects, great. I think that could be really useful. But if not, don't worry, just come up with something else. And then think about the benefits. Then think about the issues around representation and transparency and how you might mitigate against them. And issues around consequences. What might some of the consequences be? Who might be affected when this will go wrong? Okay, let me stop sharing and I'll open up the rooms and go and have a chat. And hopefully this will help shape some of your project ideas. Hello, everyone. Okay, so welcome back, and I hope you had a good discussion there about some of the ways in which you could use machine learning, and some of the benefits, but also some of the ethical considerations that we've talked about this morning. So just for the close of the session, I'm just going to ask a few groups to present some of the things they were talking about. I heard some interesting. I managed to get around a few of the rooms. I heard some interesting discussions going on. So let's bring up the wheel and spin the wheel of names and see who's going to be next up to talk to us this morning. I think it's going to be Atari ST. So does someone from Atari ST want to talk to us about your idea and where you think some of the potentials but also the pitfalls might be?
Yeah, I can do that. So our example idea was a situation where patients come onto a cardiology ward, and we give people treatment based on their characteristics before we get their results back. So kind of low risk interventions for patients who in the past have needed that type of treatment. So the benefits would be reducing the delay between admission and treatment starting and any negative outcomes associated with that. The risks obviously are people getting incorrect treatment. So our mitigation for that is kind of to do a risk benefit analysis. So only when the benefit is high and the risk is low do we apply this. There's a risk of the data set that it's trained on being very small, and also representation in the data set. So probably it would be not include many younger patients. So we would probably not apply this model to younger patients, or we would look to do some weighting and synthetic data. There are certain characteristics that we think the model would pick up on, like ethnicity and socioeconomic factors that we think might have ethical issues. And we also talked about some of the data we use in our daily jobs for socioeconomic factors for patients being quite poor quality, like postcode-based deprivation indexes and the limitations of those. I think that's all of it.
Great, no, thank you. That's a really interesting idea there, and good that you sort of picked up on some of the, the potential consequences of what could go wrong, how you could protect against that. Is this a sort of an idea that you're thinking about for HSMA, or is this a?
No, it was similar to something someone in the group had done in their trust, but adapted for the exercise.
Okay, fantastic. Okay, really interesting example. Something I hadn't sort of quite similar actually to the Samuel project going on in Pencord around the stroke girls. That's more about sort of trying to standardize decision making, but yeah, around sort of who do you treat and how do you treat. I think that's an interesting area. Brilliant, thank you. Okay, let's spin the wheel again. See who we've got next. The wheel is thinning down, so I'll have to refresh the wheel for this afternoon session. You'll be pleased to know. It's going to be Commodore 64, I think. Yeah, Commodore 64. So actually, I poked my head in and heard quite an interesting natural language processing talk going on. So do you want to share what you were talking about there?
Oh yeah, sorry, there I am. I was just seeing if I'd appear. Yes. Is it worth sharing my screen? Probably is. I'll put my notes on.
Yeah, please do.
So we talked about I've actually been doing this project for 3 years and I hadn't thought of half of this stuff, so I don't know what that says about me. So the project is we're building a natural language processing tool to classify when patients have some care. They leave like text comments. I'm sure you've all had them from the GP, how was your care, and then you can leave a text comment. And just broadly, a lot of trusts collect this and they don't have the capacity to analyze it all. So I'm building an open source tool to allow them to do that. So that's the pitch. So we talked about, it's quite a useful tool in the sense that, text is a rich source of information that we shouldn't neglect. It's obviously important to look at patient experience in terms of safety as well as in terms of making sure that they're happy with their care. and the particular implementation we're talking about is quite good from a transparency point of view, in the sense that I published all the data that trains the model and published the code as well. So there's nothing kind of hidden about it. There is something hidden in the sense that I couldn't necessarily tell you how the model worked. So we talked about that for a while. So if you looked at a particular individual comment and you said, oh, why did it classify it that way? I wouldn't know, because the model is either using TF, IDF, or word vectors, which are both mathematical representations of text. And there's no clear way that I can map between them. So I can't really explain the model to you, or not very well. We talked about a lot of the stuff is related to the data that it's based on. So, have we got data from people with low literacy? Does the model work with people with low literacy? Do we have data from people from all the different demographic groups that we see? What else did we talk about? Does it generalize across a range of vocabularies? Does it range across general different healthcare settings? That's one of our questions. So, for example, we've got ambulances this year. I haven't got any data from ambulances. You expect that would be quite different, but I don't know whether it will work for them or not. The main risks I think that we came up with were potential to waste people's time by showing them the wrong, information. The potential to produce a tool that's just used to just classify the comments into percentages and then they get forgotten about, which is something I don't want. And ironically, making it open source actually makes that risk worse, because if you want to take the code off the internet and build a model that just outputs the percentage and nothing else, then you can do that and I can't stop you. It only uses short comments, so there's not a lot of context. Healthcare data is a bit strange in the sense that people might say kind of quite strange, scary words like death or pain, but not in a negative way. So that potentially impacts the, many pre-trained models you could use, or conclusions you could draw, or, that kind of thing. And I think the other main point we came up basically is that if you're kind of bad at your job, this model can make you bad at your job. So you could use it to collect data that reinforces existing biases. You could use it to collect data in an unhelpful way by, say, putting people in a league table and saying, well, this team's got this many negative comments, but there might be a really good reason why that team's got, for example, my trust has got a high secure hospital in it where people are detained. So they're obviously not as happy as the people who are not detained. Of course they're not. And it would be really unhelpful to use this model to kind of, compare them in that way. And yeah, I think that's probably everything we said pretty much. Yeah. Oh, and also the last thing is that model performance is a very slippery concept. I think this is probably true in general in text. So the model makes a lot of kind of semantically similar mistakes, which are arguably not as bad as large semantic mistakes, but how do you quantify that? And also we're looking at adding multi-class tagging, which means each comment gets given to more than one theme, but measuring the accuracy of a multi-class algorithm is very complicated, because you've got to consider kind of, how many did it get right? And the last thing actually we didn't say that's just popped into my head now is the humans are nowhere near perfect at this. So if you look at the research, I think humans are probably about 80% accurate. So the gold standard doesn't really exist. And that's obviously a common problem with ML in healthcare generally, is that the thing you're training against actually is not perfect. And that is very much the case with this.
Yeah, no, really interesting. Thanks, Chris. It's funny you should talk about that. Actually, so we've had some really interesting sentiment analysis projects come in HSMA before. Probably one of the best was the one from HSMA 3, which was doing it basically on Twitter tweets and trying to find out how people were tweeting to every police force in the country and the kind of sentiment of what they were talking about, and then trying to drill out the things they were talking about positively and negatively. If you haven't, if anybody hasn't seen that, go and watch the HSMA 3 presentation from Mike Hill. It is astonishing what he did and what he developed on that. But we've had lots of things that have come up around that. We also did we supported a bit of work in I was about to say the hospital, in a hospital. I won't name the hospital because of what I'm about to say, but they wanted to do exactly what you're doing, looking at automatically classifying sentiment in patient surveys after the care they received, because it's such an important issue, because and I think they were, and a number of people that we spoke to were doing the same thing. They get all this information and then they end up either sitting on it, or they paid vast sums of money to people, to usually hire in people to sit down and just go through it manually. And it's such a sink in terms of the time and resource that's needed to go through these things manually, that actually having an automated process is hugely beneficial. But one thing they did find, it goes back to your point about, you know, the humans that you're learning from aren't perfect on this. We had a look at some of their data, so I think it was about we ran into this problem of it was 99% accurate, because actually 99% of people were saying very positive things, because generally people do tend to speak quite positively about the care they've received, and there is going to be a predominant bias, unless you've got a, you know, really failing service. They're going to tend to talk quite positively because they're appreciative of the care that they've had. So there is a natural bias. But one thing we did look, obviously they had a label data set, and they were labeling whether people were talking positively or negatively. And I remember having a look through, and this is why I won't name the hospital, and there were some questionable labeling of some of the comments around, you know, this was awful, you know, my dad was you know, admitted, and the care was atrocious, and blah blah blah. Positive. And that was a human being labeling that. Now I'm sure it wasn't, you know, deliberately doing that. I suspect it was because this is they probably were going through this, had enough of doing this, and were just labeling things however they liked, because it's a hugely time-consuming task. But that's the kind of data that you're going to need to train these models. So it's a really interesting point, and it goes back to our issue right at the start, where we talked about, you know, how representative is our data, and that goes back to, you know, if there are issues in that data that people, and even, you know, where you've got sentiment being prescribed by a human being, they may have their own biases that lead them to conclude, oh, I think they meant that generally in a positive sense, and it may not always be clear. So yeah, there's definitely a really interesting area, I think, and we'll touch on some of that in the natural language processing module, which will be next up in HSMA as well. Okay, let's have one more before we break for lunch. So let's share our screen. There's some fantastic ideas, by the way, coming out here. So I'm looking forward to some great machine learning project ideas for HSMA 5. It's gonna be Acorn Archimedes. Do you want to share what you were talking about for your idea?
Yeah, I think that's me.
Great.
Just start with video. So we were talking about using machine learning for interpreting surgeons' comments made against patients coming for treatment, operating theatre. And the idea is to use those comments to better predict how long a case is going to take in theatre. If we can do that, then we can better manage our day. So we know that those times are basis of what the surgeon's doing, but also who's there, do they have their favorite anaesthetist, also the comorbidities of the patient, how difficult they are anesthetically, and also might be a factor of how the hospital is as well, you know, the delays, problems with patient flow, etc. So I think the biggest concern is that potentially that data could be used for performance management. That would say, well, you're slow compared to your peers. Potentially could create a situation where the wrong choices are being made because of that kind of pressure around performance. And secondly, the data would potentially itself reinforce bias. It's just based on history of the patients that are receiving that service. So there's potential bias there, including things like when I talked about comorbidities, there might be comorbidities that are, you know, ethnicity come into those comorbidities. And let's have a look. So yeah, those are kind of the main concerns we had. I was feeling quite optimistic about this project, but now I felt a bit more nervous as we went through it. But yeah, I think it's mainly the idea that it could be used for that kind of performance management, which is really wasn't the intention. It was really just to aid decision making, if you see what I mean. But yes, a lot of unintended consequences, I think, potentially.
Yeah, no, I think it's really. I wouldn't be disheartened. I think it's a really interesting project idea. Actually, I think that there's a lot of scope for that. But it's really good that you're picking up on some of these unintended consequences. I think it's just being aware. It doesn't mean these things shouldn't be done, but it does mean that you need to be aware of how this could be misused or not used as you intended it to be. Actually, a really nice example is last year, one of the projects that I mentored was looking at, those of you who came along to the presentation event will recall that one of the projects was looking at health inequalities and carbon modelling. Part of that, and which they're still carrying on, they've got some funding to actually carry on that project now, which is amazing. But the one of the things they were looking at was basically building a machine learning model to predict which patients might be more likely to not attend an appointment. And now the intention for that is so that they can say, okay, well, can we identify, are there particular types of people who are sort of DNAing on their appointments? And therefore, to reduce health inequality, can we then do something about that? Can we reach out? Can we send out a mobile van to those communities to encourage them to attend these appointments, and get to the root of what's happening? So clearly coming from a good place. But when I went through ethics, they were quite rightly picked up on, okay, so what's going to stop somebody building this, using the model you've built, and then saying, okay, so we now know who the troublemakers are who aren't going to attend their appointment, so we'll just double book them because they're not going to turn up anyway. And I've even heard this mentioned this year as well. So be very careful about stuff like that, which you think even stuff like that where you think, this is our motivation is to reduce health inequality, but it could then be misused to something which could then increase health inequality. So really thinking about all of the potential consequences can be is difficult, but really important to explore some of that stuff. So I think so in summary, I think your project idea sounds really fascinating, and I think it's really good that you're starting to think about, and the point of this session this morning has been to get you to think about those things, rather than I shouldn't do that project because there's too many issues. In some cases, I mean, we did have a project last year where they quite rightly came to the conclusion this is an ethical minefield, and I absolutely shouldn't be doing that. But that was a far more obvious problem, I think. But where you've got stuff that could be hugely useful, but just being aware that how it could be misused and trying to protect against that, I think is the approach to take. Okay, let's stop there. Let's have a bit of lunch. So we'll resume at 1:30. And this afternoon, we're going to be talking about showing you how to build a logistic regression model to predict which patients might survive the sinking of the Titanic, and we're going to actually get hands-on with some code. So go and stretch your legs now. Hopefully that this morning though has been good for getting you thinking about some of these important issues before you get into the fun of the Python code this afternoon. Okay. Go and stretch your legs, have something to eat, and I'll see you in an hour. As I say, if you want to stay on the call, just make sure your microphone and camera are switched off. We'll resume at 1:30. Okay, good afternoon, everyone. I hope you managed to have a restful lunch break. And now we'll get back to the world of machine learning. So for the last 2 sessions, I've been teasing all this wonderful stuff that you can do, and but also this morning talking about some of the potential problems with all that wonderful stuff that you can do. But what we haven't actually done is all the wonderful stuff that you can do. So now, from this point forward in the module, we're going to get hands-on and do some of this wonderful stuff. So we're going to start off this afternoon looking at logistic regression and building a machine learning model that uses a logistic regression based model. Next week, we're going to look at, in the morning, we're going to look at neural networks, which are a fascinating and incredibly powerful structure for a machine learning algorithm. And then in the afternoon, we're going to look at using AI to generate synthetic data. But that's next week. This afternoon, we're going to start with one of these simpler methods. And as I mentioned this morning, a good approach really when you're approaching a machine learning model, machine learning project, is to start with one of the simpler models and see what kind of performance, what kind of learning performance you can get on one of those before you go into looking at neural networks. And neural networks are amazing and they will be able to do a lot. But you remember right from the very start, I've been drumming into you, start simple. So good, as with many approaches that we show you, good approach here, start with the simple model. If your simple model has very good learning performance and does what you need, then that may be enough. And so typically you then test a more complex model, like a deep learning model, such as a neural network, and see whether it adds anything. Because if it doesn't, then there's no point. Because of course, as we talked about earlier, model explainability is really important, and you lose explainability as you get into deep learning. You gain a lot as well in terms of power, but you do lose explainability. And there's things we can do around, things like Shapley values, etc. But you do still lose that sort of model transparency. So it's always a good approach to start with your and this goes for any modeling you do. Start with a simple model and then see if the more complex model adds anything. Or in the case of machine learning, you'll probably try a number of different models. But the 2 key ones we're going to show you in this course are logistic regression, which we're going to look at this afternoon, and then the neural network based structure, which we'll show you next week. But as I say, there are huge amounts more, and I'll point you to the resources, Mike's resources, which go over a lot more methods than we will cover on this course. Again, I'm gonna thank hugely my colleague Mike. Mike's Titanic online Titanic notebooks are absolutely fantastic. So here's the link in your notes. If you follow that link, you've got access to huge amounts of stuff that we don't even cover in this course, things like random forests and all sorts of other methods, and we'll go into a lot more detail about some of this stuff as well. I think there's about 30 or 40 notebooks that take you from the basics, a lot of stuff around preparing your data, which we only touch on in the course, but which you will need to do as a first step for your data. It goes through all that as well. Now, use the online materials. When you've downloaded the materials for today's session, and this applies for next week's session as well, you essentially will have an offline copy of this stuff from just over a year ago. It'll be slightly tweaked. So the stuff that I'm going to cover, the logistic regression this week, and the exercise tutorials that you'll do today, and the neural network stuff next week, I've tweaked some of that from Mike's original stuff to make it more HSMA friendly. So that'll be a little bit different. But the other stuff that we don't cover, things like random forests, etc., you've got a copy of them in your downloads from today, but I would advise you to go to Mike's link, which will have up-to-date stuff in there, and have much more than you've got, which is the stuff is still valid, but it's a year out of date. So this will give you the newer stuff for anything that we don't cover in the course over the next couple of weeks. Okay, as though you have got the older stuff as part of the download, but I would advise just using that for the particular notebooks that you're going to be looking at in those sessions. And for anything else, if you want to explore some of the other things, I would advise going on to the link here. Okay, so as I said, we want to start with a simpler model. So in the last session, last week, we talked about some key concepts in machine learning. We also learnt about my taste in movies, but we talked a lot about things like features and labeled data sets, and overfitting and underfitting, and all those kinds of problems and concepts that are so important to everything you do in machine learning. So we're going to remind ourselves very briefly of some of those core concepts, but we're also going to use those things now in order to develop a simple non-deep learning model based around logistic regression. And what we're going to do specifically this afternoon is look to see if we can build a model that will predict, based on passenger data, real-world passenger data from the Titanic, can we build a model that will predict which people will survive and which people will die? And this is a classic machine learning problem. And I saw a post went off about Kaggle in one of the groups earlier. Kaggle is a fantastic online data science resource. It's a fantastic community. It holds data sets and web-hosted data science environments and various competitions that you can take part in which companies post problems, and participants will try and develop machine learning models, sometimes to win cash prizes. So it's worth checking out. Now, the Titanic machine learning from disaster is one of the classic Kaggle competitions. There's no money for getting it. People solved this a long time ago, but it's you get a lot of people. If you have a look at that, this is where it comes from. You'll see people have posted solutions that are 100% accurate, because this has been going a long time. But basically, it's a really good one for learning the concepts of machine learning. So when you're first starting out machine learning, Titanic is a good one to start with, and that's why Mike has built all his stuff around the Titanic data set. So the challenge that was originally posted was that we want to try and use machine learning to predict which passengers would survive and which passengers would die following the sinking of the Titanic, based on various data that we've got around the passengers. And as though people compete, and you can still compete now and submit entries to see how good your machine learning algorithm is at predicting which passengers survive and which don't. Now we're going to come back to the Titanic data in a bit, and I will talk through that data. But let's just very quickly remind ourselves some of the things we talked about last week, because we're going to now need to put these things into practice. So one of the key things we talked about were features. We said that when we want to teach a machine to make a prediction or classification, we're essentially wanting to get it to predict an output, which we call a label in machine learning, given a set of inputs. And these things are referred to, the inputs are referred to as features. So it's a bit, as I said, it's a bit like a table, and you can imagine various columns containing different pieces of information about our individual records. Those are our features. So can we, given this information, predict what the output would be? So given these pieces of information about a patient, can we predict whether they've got a certain condition, or can we predict whether someone's likely to reoffend based on the nature of their crime, their original crime, whether they served a custodial sentence, all these kinds of things? Can we, from this, predict this? We talked about how features are weighted in machine learning models, such that some features will become more important and some less important. We touched on that a little bit this morning in the ethics discussion as well. So we looked at this example of when trying to identify someone as a Pencordian or not, and trying to identify what might be the important features that most drive that prediction. We also talked about train test splits, So we said that commonly we would at least want to split our data into a training set and a test set. We have our labeled data set. Remember, a label is an output in machine learning terminology. And so a labeled data set is a data set in which we have both the inputs, the features, and the answer, the output, the label. And so we carve that up into a training set and a test set. When we go on to neural networks next week, we'll come back to we talked also about having a validation set. That comes in more with the neural networks, and we'll talk about that next week. But for now, we're just going to carve our data into training and test data. We use the training data to train the machine learning model, the algorithm that we're building. We use that to train it, to fit it. Remember, that's what we call training in machine learning. It's known as fitting a model. And so we use that data to train it. And then once it's been trained, we use the test data, which it hasn't yet seen, in order to see how good it is and get a sense about how generalizable the model is. Because, of course, we also have this problem, which is a very common problem in machine learning, the problem of overfitting, where essentially the model has learned things that are too specific to the training set, to the training data. And so it's learned to fit a line in multi-dimensional space. Here we present it in 2 dimensions because I don't have a multi-dimensional monitor. But here's an example of where we've fitted a line that is trying to identify the dividing line between yes and no classifications, and it is too specific to the training data. And in fact, we should be looking at, oops, sorry. Oh, for some reason I can't go back. There we are. We should be looking at a line probably somewhere around here. But it's got everything right in the training set. But when that's come to be used in the real world, we'll likely find that it's not very good, because it's just learned things that are too specific to the training set and therefore becomes useless, because if it can't make predictions beyond the training set, then it's a useless model. We also talked about various performance metrics, the 3 key ones being accuracy, precision, and recall. We'll also this afternoon talk about receiver operator characteristic curves as a way of assessing model performance and potential performance. We'll talk about that a bit more later. But the 3 key ones, the headline ones, accuracy, remember that's the percentage of predictions that the model makes correctly in the test set. So it's basically how often am I right? Whether they guessed one thing or another, was it right or not? Okay, and so accuracy on its own can be a bit misleading, and we talked about how that can be misleading, because if we've got 100 records and only one of them contains the thing we're interested in, then a machine can learn. If I just say so let's say the one thing we're interested in is somebody getting admitted, if the machine can very easily learn, I'll just say they're not going to be admitted because I'll be right 99% of the time because I've got an underrepresented class. So accuracy on its own isn't particularly useful. We need to use it in combination with other things. And those other things include precision, which, remember, precision is when I say something is of a particular classification, how often am I right? And recall says, how many of that classification did I correctly find? So precision says, when I say it's this, how often am I correct? Recall says, how many of them did I find out there? Okay, so that's a brief reminder of the key concepts that we covered last week. Now let's move on to talk about logistic regression. But let's first talk about what we mean by regression. So regression simply means a set of approaches in which we're trying to predict some output value given one or more input values. If you're come from a stats background, you will be familiar with regression, and you'll probably have a slightly different terminology to those who are machine learning modelers. But it's basically the same sort of thing. So the output value in stats is usually referred to as the dependent variable, sometimes the outcome or response variable. And that's the thing we're trying to predict. Remember, in machine learning terms, that's the label. And the input values, which in machine learning we call the features, are referred to in stats as the independent variables in a regression, sometimes called the explanatory variables. And those are the data values from which we're trying to predict the dependent variable. So in stats terms, in a regression, you're trying to predict the dependent variable from your independent variables. In machine learning terms, we're trying to predict the label from our features. So examples of regression might be where you'd use it. You might be trying to predict the level of revenue that you get from a certain amount of advertising spending to assess, how much is worth putting into advertising. Predicting house price from the size of house, etc. These are the sort of things that regression can be used for. So that's regression. Now let's talk about linear regression. So linear regression is a type of that regression where essentially what we're trying to do is fit a straight line that best fits the data points. So you probably all remember this from school, that we did a little bit of linear regression, and a linear regression line is described using this equation, y equals a plus bx, where y is the dependent variable, that's the one we're trying to predict. A is the intercept, i.e. where the line cuts through the y-axis at x equals 0, so where it hits over here. B is the slope gradient of the line, indicating the steepness. And x is the independent variable or feature in machine learning terms. And a common method for fitting a linear regression model is to use something called least squares regression, where the line of best fit is the one which minimizes the sum of the squares of vertical deviations between data points and the line. So in other words, if this is our line, we need to find the line such that if we square the distances between these things, we square them because they could be above or below. We square them and then add them all up, and we're trying to find the line where that number is reduced, thereby finding the line of best fit, the one where the distances between these points and the line is the least. Okay, because that's essentially what we're trying to do. We're trying to find the best fit. What function describes this data? That's all it is. Now, of course, we're showing this in 2 dimensions here. That's fine if you've got just one independent variable, but of course, if you've got more than one independent variable, then this graph will be in more than 2 dimensions. And of course, in machine learning, you may be dealing with hundreds of features. So you essentially the same thing would be happening, except in 100-dimensional space. But that hurts our heads, so let's think about it in 2 dimensions and just know the same principle applies in the multiple dimensions that we can't really visualize. So that's linear regression. Now let's talk about logistic regression, which is the type of model that we're going to use. So with logistic regression, what we're trying to do is predict the probability that a particular record, a particular entry with its own set of inputs, features, belongs to a given class. So that matches the kind of thing that we're talking about. We want to take some inputs and predict whether it belongs to this class or to this class. So we could use logistic regression to predict things like the probability of passing an exam against mock exam grades. Or, as is appropriate for this session, the probability that a passenger on the Titanic with a given set of features would survive the sinking. Okay. So logistic regression is typically used in machine learning for classification type problems. Given these set of inputs, essentially outputs a probability, and that probability is compared against a threshold. We'll talk more about that. And if it's above a threshold, we say it belongs to this class. If it's below a threshold, we say it belongs to this class. Well, for binary classification, which is most of what you'll be doing. The classes in the Titanic data will be survived and died. Do we classify this patient as a survivor or somebody who died? As I say, the simplest form of logistic regression considers only binary classes. Is it this or this? Which is will cover most of the stuff you want to do. There are more complex forms that allow for more than 2 classifications. We're not going to worry about those here. Most of the stuff that you will do will be binary classification problems. Now, The logistic regression is called logistic regression because of the function that defines the regression line. So when we had linear regression, we had basically a straight line. We're finding the line of best fit, a straight line of best fit. Here, the function that defines the regression line is the logistic function. And the logistic function is an example of a sigmoid function. And a sigmoid function is one which has an S-shaped curve. Probably it's rattling around in your head some from your old maths classes, those are what sigmoid functions are. And we can set up a logistic function to take any value and map it to a value between but never reaching 0 and 1. And that makes it really useful to generate outputs that represent probabilities. Okay, so here's the maths behind it. Again, don't worry too, and we never dive deep into the mathematics in this course. You don't need to understand the mathematics. This is just to get the gist of what's happening. Okay, so essentially the logistic function here, we can set that up so that fx is the output. In other words, it's a function of x. So given x as an input, doing something to x to create the output. And the function that we have is defined here by L, which is the maximum value of the curve. If we set that to 1, then we can use this function to map between 0 and 1, therefore emulating probability, which is what we want to do. We want to say, what's the probability that it belongs to this class as opposed to this class? The nearer it gets to 1, the more likely they survive. The nearer it gets to 0, the more likely they die. And then we have that over 1 plus e, then the natural number, Euler's number, to the power of minus k, which represents the steepness of the curve. And then in here we have x, which is the value to be mapped. That's your input, your feature value. And x0, which is the midpoint of the sigmoid curve. That's the point at which it intersects with the y-axis. Don't worry about the details of that. Basically, just know that's essentially we can set up a logistic function very easily to output a number between 0 and 1, thereby allowing it to emulate a probability. So here we can see the clear difference between a linear regression and a logistic model. So linear regression, we've got we're finding a straight line of best fit. With a logistic model, we've got values between 0 and 1 on our S-shaped sigmoid curve. And essentially everything down here belongs to class 0, everything up here belongs to class 1, and then everything in the middle is essentially up for grabs. And depending, we'll talk about the threshold, but depending on where the threshold is, we either say it belongs to this class or to this class. And the closer it gets up here, the more likely it is to be a class 1. The further it is down here, the more likely it is to be a class 0. That's what we're doing. Now, what a logistic regression does, that's a logistic function. What the logistic regression does is it combines the logistic function, the S-shaped curve we just looked at, with a linear function, the straight line thing, that has weights or coefficients, if you're a statistician, associated with each input value. Because remember, weights are really important in machine learning. So in other words, again, starting to get into deep maths, you don't need to worry about it. Basically, it's saying the equation will fit a linear model with weights for each input, each of our features, so we know what is contributing the most to our prediction, and then converts that using a logistic model to output a probability between 0 and 1. And then that's what allows us then to determine whether something belongs to one class or another, because we get a probability as the output. So we combine linear model with logistic model, and we get a logistic regression. There's the maths if you want to know about the maths. Okay, so that's what logistic regression is doing. We take the linear model, which has we encode the data about the weights for each feature, and then that's put into a logistic model, logistic function, sorry, which will output a probability, which you can then use for classification. So how do we do this in Python? Unfortunately, you don't have to write those equations, because there's stuff that does this for you. it's actually really easy to do logistic regression in Python. And we can use a library. There's many libraries available, but one of the most popular for this kind of stuff is scikit-learn, or sometimes known as sklearn. This is a widely used, well-established machine learning library that contains lots of different machine learning algorithms. And it's also got lots of methods that we can use that allow us to easily split our data into training and test sets and pre-process our data in the correct format for various different algorithms, etc. So it's really useful. Now, Anaconda already comes with scikit-learn installed. So if you've installed Anaconda, this should be on there. I am flagging this. Hopefully you read my message, though. I know if you went through the process of upgrading Spider and found you no longer had NumPy installed and pandas installed and matplotlib installed, and you had to pip install them, you're probably going to have to do the same thing with this. You'll have to pip install scikit-learn, and I posted the instructions for doing that. It's the same principle. So assuming that it's installed, though, you can import the logistic regression module that will allow us to build logistic regression models. And we just import this as such from sklearn.linear model, import logistic regression, and that will allow us to access the logistic regression stuff. Now, if we assume for a moment that our data is processed in the format we need it to be. When you do this in the real world, it won't be. Okay, it will be in your model that you do this afternoon, but when you come on to do this in the real world, it won't be. And there are lots of notebooks that we've got that show you how to pre-process your data. So all of that stuff is in Mike's materials. It's all, getting it into pandas and formatting it correctly and dealing with missing values, because you can't have missing values, etc. We'll cover all of that separately. But let's just assume for the moment that all of that pre-processing has been done. There's basically three things that we need to do with our data that's been pre-processed before we give it to the logistic regression model. The first is we need to divide the data into our features, our inputs, and our labels, our outputs. Then we need to divide the data into training and test sets. We need to carve our data up. So we've got, this is the data you're going to use to train. This is the data we're going to use to check how well you've learned. And then we're going to do something called applying feature scaling, which is basically where we try and make sure that all of our feature data values are on a similar scale. So let's look at each of those things in turn. So first of all, we need to divide our data into features and labels. So features, when we do this in Python, we denote that with an uppercase X. The capital letter here signifies there are multiple features for each example. Okay. And we divide that into features and our labels, and we denote that with a lowercase y, the lowercase indicating that there's a single label for each example. Okay, so this is a common notation that you'll see. Uppercase X is features or inputs. Lowercase y is your label or output. You'll get used to seeing these things. So let's imagine that our data is stored in a pandas data frame called data, which it will be when you come on to do the exercise. So that's good. Mike's already done the pre-processing, but you'll see in that notebook when you come on to that, that he takes you through, if you go to an earlier notebook, how he did all that, how he got it and pre-processed all that data. So when you come on to do this for real in your own projects, you can see how you would do all that stuff. It's not complex, it's just time consuming. So, but let's imagine Mike has kindly done all this for us, which he has. We've got a pandas data frame called data, and our label is stored in a column called outcome. So we've got various columns in our data frame. Each of those columns has a column header, which represents some aspect of the data, one of our each feature. And then we've got one of them that says outcome, and that's our label. That's the thing we're trying to predict. So if we've got that, then it's very easy to store and divide our data into features and labels. To grab the features, basically, we want all of the pandas data frame apart from the column that says outcome, because our features are everything apart from that column that we're trying to predict. So to do that, because it's a pandas data frame, we can do this really easily. We say the name of the data frame, in this case data, dot drop, and we can tell it to drop a column. Axis equals 1 means drop a column. Axis equals 0 is drop a row. And we give it the name of the column we want to drop, which in this case is outcome. So that line of code basically says from the pandas data frame called data, drop the column called outcome. But give me everything else. So then X becomes all of that data frame apart from the last column. So X is now a data frame minus the last column. And Y, our output, our label data, is that column. It's the opposite. So here we just grab that column, and you're used to seeing this for pandas data frame. We just get the name of the data frame, square brackets, and the name of the column we want. So X is everything but the outcome column. Y is the outcome column. So now we've got two pandas data frames, one called X, one called Y. X stores all our features. Y is the labels that we want to try and predict. That's pretty easy. Then we need to split our data into training and test sets. Again, because we're using scikit-learn as a library, this is incredibly easy to do. So we've actually got a module in scikit-learn that allows you to do that. And we can import this from sklearn.model selection, import train test split. It's a really useful module. We can import that, and then basically all we need to do is this line of code, and it'll do it for us. It'll break up our data into training and testing set. So I'll come back to the bit on the left, but let's just look at the bit on the right. All we do is we call train test split, and we give it X, our features, which we stored a moment ago, Y, our outcomes, our labels, which we stored a moment ago, and we give the size of the test set. So here test size equals 0.25. So essentially we're saying carve off 25% of that data to be a test set and use everything else for the training set. Okay, so it'll do that automatically for you. Now the way it returns that is in this order. It will give you the input data and the output data for both the training and the test sets, because you've now got 4 kinds of data. Once you run the train test split, you split your feature data and your label data into training and test sets, and it'll come out in this order. The training data for your inputs, the test data for your inputs, the training data for your outputs, and the test data for your outputs. And we typically you can call them whatever you like, but this is commonly used. Xtrain being training data for your features, Xtest being test data for your features, and so on. So Xtrain, Xtest, Ytrain, Ytest. And it'll come out, it'll be returned by this function in that order. So now we've got training data and testing data for each of our features, our inputs, and our labels. So then the other thing we want to do is to scale our feature values. Now, you might think, why do we need to do that? Let's think about an example. Let's imagine we've got the following kinds of features in our data that we're using to try and predict something. We've got age, the number of admissions to hospital, and mean daily calorie intake. Now, let's think about the kinds of ranges of values you might expect to see for each of those things. Well, age, probably up to around 100. But depending on the kind of data you're looking at, you might get peaks around elderly people. Depends on the data you've got. Number of admissions to hospitals, probably likely going to be less than 10 for most. And mean daily calorie intake, you're going to be talking in the thousands. So these are features that we want to use to predict something, but the values of those features are on very, very different scales. And that can be a problem. The problem being that, well, twofold really. The first is that if we try and train a model based on features with vastly different scales, we tend to get poorer learning performance, because what the algorithm tends to do is tends to give more weight to features whose values have higher magnitude. So naturally, in this example, the mean daily calorie intake would tend to get a higher weighting, even if it's not truly something that is a more powerful predictor because of the scale of value. It's thousands compared to tens or maybe 100. And it also means if we keep them all on that scale, on these vastly different scales, it's very difficult to compare the weights between different features, because some of the weights mean much more to features with lower values. So it makes it a bit tricky. So the way in which we approach this is to try and put everything on a similar kind of scale without losing the important information that's in there that we're trying to learn from. And the two most common ways in which we try and scale our feature values are normalization and standardization. So normalization is where we rescale all of our values so that they fall between two values, and typically that's between 0 and 1. Sometimes it's between -1 and 1, but usually it's between 0 and 1. Okay, and this is also, you'll also hear this referred to as min-max normalization. It means basically take all of the numbers in your data and put everything on a scale so that everything fits between 0 and 1. That's min-max normalization. And then the standardization, and standardization is slightly different. There, we center all of our values around a mean of 0 and with a standard deviation of 1. So essentially put them onto a distribution where we have a mean of 0 and a standard deviation of 1. So we don't, unlike normalization where we have a bounded range, we say nothing can be below 0 and nothing can go above 1. It all has to fit between those. We don't have that bounded range with a standardization, but it does mean that most of the values, the vast majority of the values, because we've got a mean of 0 and a standard deviation of 1, are within a controllable range. But it allows us also then to fit in outliers a bit more naturally. So let's talk about normalization first, min-max normalization, where we want to put everything, all of our values between 0 and 1. We can do that using this equation here. And what this is basically saying is to get a normalized value for a data point, which is our value x here, you subtract the minimum value in your data from that data point and divide it by the range of values, the maximum data value you've got minus the minimum value you've got. So if we imagine our data contain the values 2, 5, 7, 9, and 100, how would we normalize the value 5? So 5, instead of staying as 5, would become this. We would say 5 minus 2, which is the lowest value in our data set, divided by the range, which is the highest value, 100, minus the lowest value, 2. So we've got a range of 98 in our data. So that gives us 3 over 98. So that becomes 0.03. So the value 5 normalized would become 0.03. And we can see how this makes sense, because then if we look at the highest value in our data, our highest value is 100, that'll be normalized to 100 minus 2, which is our lowest value, divided by 100 minus 2, which is our range, which is 98 over 98, which is 1. So the highest value has a value of 1. Similarly, the lowest value, which is our value of 2, would come out as 2 minus 2 over 98, which is 0 over 98, which is 0. So the lowest value would be 0, and then everything else would fall in between. So 5 is much closer to 2 than it is to 100, so 5 gets normalized to 0.03. Whereas if we had a value near 100, it would be much closer to 100. So how do we do this in Python? There's different ways you can do it. You can do it manually, or you can do it using pre-built libraries. Reality, you probably do using pre-built libraries, but we're showing you both methods to get you used to doing this. So let's imagine we're min-max normalizing a NumPy array of data values. What we're going to do here, we're just creating a NumPy. So this line of code basically just generates a NumPy array where it takes 1,000 samples for 1,000 samples and 2 columns, features if you like, from a normal distribution with a mean of 50 and a standard deviation of 10. So all that line of code is doing is just giving us some random numbers from a normal distribution in 2 columns and 1,000 samples of it. So that's all it is. So obviously in your real world models, you wouldn't have that. You'd have your actual data. But this is going to be, we're just randomly generating some data here. So to do it manually, we remember if it's stored in a NumPy array, one of the beauties of NumPy is that we can perform a mathematical operation to an array, and it'll automatically apply to all elements of the array without having to go through a for loop. It's one of the great advantages of NumPy. And when we looked at NumPy how much more efficient it is than using a standard loop. So here we can just say, well, it's x norm, our normalized version of x, which is our original data, is each data point minus the lowest value in the data divided by the range, the highest value in the data minus the lowest value. In other words, that equation I just showed you. That's how you'd apply it to a NumPy array. And we can see if we have a look at the first 5 entries from the original data. This is the randomly generated data that we created. And then let's look at the normalized version of that data, and you can see everything falls between 0 and 1. So that's one way, or you could do it using the min-max scalar library, and we can do that with the same data. So same thing again, the numbers will be different because each time it's going to generate 1,000 different numbers. So we import min-max scalar from scikit-learn .preprocessing. And the way in which we do that here is we just say, we create a new scalar object. We say we want a new min-max scalar. I'm going to call mine scalar. Then I call the fit method of that scalar, and I pass in the data I want to fit. And then I call the transform method on the scalar, passing in the data that I want to transform, and that will return the normalized data. So those 3 lines of code will do it for me. Create a new scalar, fit it to the data so it can get the right fit, and then apply the transformation. Those 3 lines of code, that'll always work. So again, here's your original data. Here's the normalized data. So that's normalization. Put everything on a scale between 0 and 1. Then we've got standardization. So standardization, remember, this is where rather than put everything between 0 and 1, we're going to put everything on a scale such that the standardized data has a mean of 0 and a standard deviation of 1. So it has a more manageable spread. We can do that using this equation here. And what this equation is basically saying is we take each value, our x, we subtract from that the mean of the data, mu, and we divide that by the standard deviation of the data. So data point minus mean divided by standard deviation equals standardized data point. Let's look at this in practice. So again, let's look at our values 2, 5, 7, 9, and 100. So the mean of those values is 24.6, and the standard deviation is 42.23. So how would we standardize each of these values? So 2, we would standardize as 2 minus the mean, 24.6, divided by the standard deviation, 42.23. So 2 would become minus 0.54. 5 would become minus 0.46. 7 minus 0.42, 9 would become minus 0.37, and 100 would become 1.79. And if you take the mean and standard deviation of these standardized values, you'll find the mean is 0 and the standard deviation is 1. And you can see we've got a cluster of values that are all pretty low and this really high value in our data. So all the low values are sort of tucked in the negative side of our x-axis, and then we've got this much higher value out here, so we can still deal with that higher value, but it's in a more manageable distribution. And again, as with normalization, when we're doing this in Python, we can do it in different ways. We could do it manually, or we can use a couple of different approaches in the scikit-learn library. One to use the preprocessing.scale function, and the other to use the standard scalar function. So to do it manually, we basically just need again to replicate that function that we just showed you here, that equation. So again, I'm generating a random NumPy array as I did before, and I'm just replicating that equation. So x minus x dot mean divided by x dot std, which is the standard deviation of x. That gives me the standardized version of my data, and we can see that here. Here's our raw data, here's our standardized data. If you want to use the scale function of the pre-processing module, we import pre-processing from scikit-learn, and we just very easily just call pre-processing.scale and pass in our data, and that returns that data that's been standardized. Or we can use the standard scalar module. We import standard scalar from scikit-learn.preprocessing. Again, we've got our same random data here. I create a new scalar object, and then I call the fit transform method and pass in the raw data. So there's different ways you can do it. I'm just flagging up a few of the different ways that you will see this done. Okay, so you're probably thinking, okay, I get the idea why you'd want to put things on the same same sort of, you know, more manageable scale. But there are two approaches. When should I normalize and when should I standardize? Because they're quite different. And it's a good question. And there aren't necessarily any hard and fast rules, and you might want to try both. But generally speaking, linear regression will tend to work best with standardized data, where you're putting everything on a scale where the mean is 0 and the standard deviation is 1. And neural networks, which we'll look at next week, tend to work best with min-max normalized data, where you put everything on a scale between 0 and 1. So those tend to be the rules. There are some, I believe, random forests don't use scaling at all. I think that's mentioned in your notebooks as well. So I always think of it as in my head, neural networks are normal. That's my little saying that I say to myself. Neural networks are normal, and I remember normalization for neural networks and linear regression tend to use standardization. Another important point to say when you're standardizing, which you're going to do today because we're doing linear regression, when you standardize the training set data and use the training data's mean and standard deviation to standardize the test data rather than the test data's mean and standard deviation. And that's so that you can ensure the test data is on the same scale as the predictions generated by the model. So it doesn't, for normalization, doesn't matter because everything's on a scale between 0 and 1. But obviously the absolute scale of a standardization can vary because all you're specifying is the mean is 0, the standard deviation is 1. But you can have a much wider spread as well. So it just ensures everything's on the same spread. So you standardize the training set data and use that new scale for your test data. So once we've done those three things, we split our data into features and labels. We split our data into training and test sets, and we scaled our features. Then we're ready to fit the model. That's basically doing the training, doing all the interesting stuff. And I'm sorry to disappoint you if you think that's going to be, you know, where you get into the meat of the code, because those 2 lines of code will do it for you. It's actually really easy using scikit-learn. So all we do is we say, I want a new model, is a logistic regression model, and then you call the fit method of the logistic regression model. Remember, fit means train in machine learning. And we pass in the training data for X, our features, and the training data for Y, our labels. And it does it. That's it. Create a new model, call the fit method. That will do your logistic regression. Now, just to point out here, because I've in this example I've said X train and Y train. In reality, you've probably you'll have needed to standardize your data. So you've probably called it something like X train STD or Y train STD or something like that. And you'll see that in Mike's notebook when you get onto that in a moment, because you probably want your original X training data that hasn't been standardized stored separately. You could overwrite it, but generally you want the raw data separate so that you could then try it with normalized data or do something else with it. So in reality, that would probably say model.fit X train STD, Y train STD, something like that, or whatever you've called it. You'll see examples of that this afternoon. Those two lines of code train our model. Once it's been trained or fitted, then we can use our model to generate predictions, which is what the whole reason for doing it. And that allows us then to test the accuracy and various other metrics, precision, recall, etc., on both the training set and the test set. And to generate predictions from a fitted model using the scikit-learn library, we just use the predict method. So model.fit says train this model. Model.predict says get some predictions. So here we say model y, I've called it y pred train. So these are the predictions for the training set, and I get that through model.predict, and I pass in the x training data, the input data for the training set, and to get the predicted labels for the test set, I say model.predict and then pass in the test data inputs. And that allows us then to see the accuracy of both the training set and the test set. And we generally expect the training set to be a bit higher than the test set. And if it's much higher in terms of the performance, then it likely means we overfitted. Okay. Oh, I'm actually a little earlier than normal. That's good. So what I want you to do, you're going to we can either take a break now, we can take a break a little bit later, it's up to you. But you're going to have until probably about 3:40-ish, but we're a little bit early, so if you get through this quicker, great. But I want to make sure that you've got plenty of time to properly absorb this and do it. So we'll say 3:40. That's what I've timetabled. So let's go for that. So what you're going to do is you're going to go into groups. And the first thing you're going to do is going to work through two Jupyter notebooks that you've got called HSMA Tutorial 1 and HSMA Tutorial 2. So let me first of all bring those things up so you can see them. So in the repository you've got that you've downloaded the materials from for today's session, you've got this. And this is what I was talking about. These are the materials from a year ago from Mike's Titanic books, but with some of the notebooks, the ones you're going to be using, that I've adapted and made more HSMA-like. Okay, so you're going to first of all go with tutorial 1. And what I want you to do, get somebody to share the screen in the group, and then you're all going to read through it. And then, so a lot of this covers the stuff that I was just covering before. And then you're going to start going through the code. So I want you to look at each cell, look at each line of the cell, make sure you're understanding what it's doing, then run the cell, okay? And then move on. And make sure everybody's following along with how this stuff works. So the first tutorial will take you through the stuff around normalization and standardization, some of the stuff that we were just talking about, and you'll see a plot with some funky little plots to see how that works. And you'll see that in practice, how it looks. Then you'll move on to, so that's a fairly short tutorial, there's a little task at the end, a mini task, fairly short tutorial. This one's a longer tutorial. This in tutorial 2 is then where you get on to using the Titanic data, and you're going to see if you can build a logistic regression model to predict whether people will survive the sinking of the Titanic. And it gives lots of information here about the data, and you'll be able to view the data. Some of the code will show you the raw data so you can see it. But here's how the Titanic data is made up. You've got whether they survived or not, that's your label. 0 being no, 1 being yes. The ticket class, P class, the sex, age in years, number of siblings or spouses aboard the Titanic, number of parents, children aboard the Titanic, their ticket number, their passenger fare, their cabin number, and the port of embarkation, whether it's Cherbourg, Queenstown, or Southampton. Okay, so that's your data. Mike's done the pre-processing to get it in, and you'll see that in this notebook to get it into the format that you'll need it. And then you'll kind of take it from there. So you'll gradually work through, and you'll do the same thing again. Read through each bit, read through each line of each cell, make sure you all understand it, run it, have a look at what it's doing, make sure you're thoroughly understanding what's going on in each of these bits. Then, once you've done that, once you've completed both the tutorials, you're then going to move on to this exercise here, where you're going to then build your own logistic regression model to look and see if you can predict whether a patient is going to receive, this is clot busting treatment, it's meant to be clot busting treatment for stroke. Okay, so this is based on some real world data that Mike's put up. This code will download that from his GitHub repository, put it into a nice pandas data frame and do all that for you. It's all nicely formatted. And then you'll have a go at writing your own code to create a logistic regression model. And what I want you to do, and I'm going to put this link in Slack. Once you've done that, I want you all to share your solutions here. So the HSMA 5 student GitHub organization, you've all been made members of that. I've upgraded you this afternoon because I realized you were on the wrong permissions, which is why I think we had a few problems before when we tried to do this with the coding club. You've now got the correct level of permission. So we've got this repository that I've created here, 7C logistic regression stroke. So one of you from the team, I want you to upload your solutions at the end of the session or the end of the exercise up here. So again, all you need to do, we haven't shown you proper GitHub yet, but if you click add file, click upload files, and drag and drop your file. Okay. What I would do, actually, just thinking about it, because you're all going to put it on there, I would probably put it into either separate folders or name your notebook with the name of your group. So if you're Commodore 64, put Commodore 64. If you're Amiga 500, put Amiga 500 as the name of the file, etc. So put them up there because we haven't got a solution for this exercise, because you're going to have a go at doing this and seeing what sort of model you can build. So these will be your solutions. Okay, any questions about any of that? No? Great, okay. In which case, let's stop there. Probably going to have a 10-minute break now, I would advise. My Zoom's crashed. Hopefully you can still hear me. I will just reboot my Zoom, then I'll open up the breakout rooms, and yeah, go and stretch your legs, but then go and have fun and see if you can build some logistic regression models whilst I throttle Zoom. Okay, welcome back, everyone. Yeah, I wanted to give you a bit of extra time on that, because I think by the time of the exercise, most of you were either just about to get to the bit where you were going to do the stroke model or just started it. So I just wanted to make sure you had a bit of time to at least start that, and in some cases complete it. So don't forget to upload your solutions to the GitHub. I can see one up there already. Well done, Apple Mac. I can see that one's oh, and ZX Spectrum I've just seen pop up 43 seconds ago. Fantastic. So upload I think it's a great way to be able to share your stuff so other people can have a look at that as well. And it's also a great reminder for yourselves that you're, again, let's just pinch ourselves and remind ourselves that it was only about 6 weeks ago that you were printing the words "Hello World" to the screen, and you're now building logistic regression models in Python. That's quite a leap. So you've come a long way. So great to see so many of you getting on well with this. I think it's one of those you probably have to go back and have a look at some of the notes to get your head around it. But just to basically explain, because I think this came up a couple of times, what you're essentially doing with a logistic regression model is it's fitting a line to try and separate, in this case, survived and died in the Titanic example, in multi-dimensional space. And that line is what that model is then going to use to say, for a new entry, when I look at a passenger, I will look at that line and I'll be able to work out it'll output a number between 0 and 1. And if it's closer to 1, then I'll say they survived. If it's closer to 0, then I'll say they died. And the default threshold, which we're going to look at in a moment, is 0.5. So if it's above 0.5, we'll say it's a survive. If it's below 0.5, then they died. For those who managed to get onto and complete the stroke exercise, how did people get on? What sort of accuracy were you getting on that?
We had 77% initially, and then when we changed the test size to 20%, we got an 82% accuracy.
Was that on the training set or the test set, or
like in the train test split model, when we reduced the test size to 20%, the model accuracy went up to 82%. Oh, that was for the, I'll just check.
That was for the test run.
That was for the test set, yeah.
For the test set, yeah.
Brilliant. Okay. So that's something you can play around with. I heard that a few times, saying, well, how do we get this to improve? And there's various different things you can do, one of which we're going to talk about in a moment, or two of which actually we're going to talk about in a moment. But remember, the logistic regression model is a fairly simple model. You're essentially creating this, I would say simple, you're creating a line in multi-dimensional space using a logistic function, which that's simple in machine learning terms. But it does mean that, so it's simpler because it means that we can unpick it a little easier. But it also has the drawback that means for more complex relationships, it might be that it's not quite good enough. And that's why you then look at whether deep learning, which is what we're going to come on to next week with the neural networks, whether that can help. And next week, when we look at neural networks, you'll see there's lots you can play around with in a neural network. Whereas with a simpler model, obviously there's less to it. So you can do things like playing around with the features that you put in, taking things out, putting things in. You can change the threshold. You can look at the train test split. I'm going to cover a couple of those things in a moment about how you can do those things. But there's less you can play around with because it's a simpler model. But with the neural networks, unlike today, where the logistic regression, where you're essentially fitting a line in multi-dimensional space and saying, that's the line that describes my data, that's the line of best fit, and therefore I'll make predictions for any passengers. I will read off what their entry would be on that line. When we go on to neural networks next week, you'll see that actually, rather than fitting a line in multi-dimensional space, we actually replicate the workings of the human brain and use that in order to get better and better and better in this kind of weird, magical black box thing. So it's quite a different way of approaching things. It's a more complex model, which means there's more to play with. And also, because of that, it's a bit less transparent in terms of how the prediction is working. But they tend to be much more powerful because of that. But let's just move on to the final bit for today, because there's a couple of other things that are really important whenever you're doing any machine learning, and these are things that you can play around with in a logistic regression model too. So let's bring up the slides. Okay, let's first of all talk about stratified k-fold validation, which is a fantastic name. Let's explain what that means. So far, when we've split our data into training data and test data, we've made one split. We've randomly selected a percentage of our data to carve off to be training data, and then to be test data, and use the rest to be training data. So in the stock example, we said carve off 25% of it, and we use the built-in method in scikit-learn. It'll just randomly pick 25% of your data to be your test data, and it'll leave the rest to be the data you use for training. And obviously, we just heard, one of the teams then played around with that percentage. And of course, that also means that you all got slightly different accuracy results, even though you were carving off the same amount of data, because it's randomly picking that. We didn't fix it. It's randomly selecting that data. So you get slight differences, and you even sometimes get slight differences in terms of the weightings of the features, because it's seen slightly different, was use slightly different data to train. And that brings us on to a potential problem with this, in that the actual split that you make randomly might not be a good split for training, and you might get a misleading assessment of the performance of that model, how accurate it is. Just think back to when we looked at discrete event simulation a couple of weeks ago. We said we don't just run the model once. You might have a run of good luck or a run of bad luck. We run it lots and lots of times to get a more representative example. And the same holds true here. And to do that with a train test split, we can use something called stratified k-fold validation. So to explain this, I'll first explain what k-fold validation is. So k-fold validation is where we repeat the model training and testing a certain number of times, k times, such that all of the data is used once and only once as part of the test set. So in other words, all of the data that we've got gets an opportunity to be the thing against which we check rather than the thing against which we learn. So we avoid that problem of maybe we've randomly selected our training data and it's not the best data, it's not the best way to split it for training. So we avoid that problem because everything gets to be part of the training and everything gets to be part of the test, but only once. Sorry, only once as part of the test set, I should say. Now, in stratified k-fold validation, we also ensure that the balance between different outcomes, so in the Titanic data, that's number of people that survived versus number of people that died, that balance is retained for every split we do. So if it's a 60-40 split, so if 60% of them survived, 40% of them died in the data as a whole, then the stratified k-fold validation will ensure that every time we take a split, that balance is maintained. We always have a 60-40 split between survived and died. Okay, so the key thing here is that you are repeating the training and testing a number of times, and you're carving up the data into training and test sets differently each time, so that the tests, everything gets an opportunity once and only once to be part of the test set rather than the training set. And the stratified bit comes in to make sure that as when you do that, it makes sure that the balance of outcomes remains the same for each split. So that's stratified k validation. And there's a workbook, so you won't get time to have a look at this today because we've overrun, but I'll give you the links to the notebooks. Have a look through and it will guide you through how to do a stratified k-fold validation. It's actually really easy to do it. Okay. The other important thing I wanted to flag up was something called a ROC curve. So a ROC curve stands for receiver operator characteristic curves, and these are really, really useful when we're trying to better understand the performance of our machine learning model. They're a bit more complicated to explain, so I will take this slowly. Just so that you can, because you have to sort of read this a few times to let it sink in. So essentially what they do is they plot two things against each other. One of the things they plot is the true positive rate. So that's the proportion of cases that we correctly identify as positive out of all positive cases. So ones where we say, so if it's in the Titanic example, positive, I mean survived. So where we say they survived and they did survive, that's a true positive. We got it correct. And we said they would survive and they did. That's also known as sensitivity. Okay. We plot that against the false positive rate. So the false positive rate is the proportion of cases that are incorrectly identified as positive out of all negative cases. So ones where we say that they did survive, but they didn't. So it's that out of all of the cases where they did actually die. How many of the cases where they did die did we say actually they survived? And that is 1 minus the specificity, or it's the false positives divided by the false positives plus the true negatives. Don't worry, I'll come back to this in a moment. It'll make a bit more sense. So a false positive rate of 20% would mean that 20% of cases that are negative, where they died, we would say that they survived. So we incorrectly classified them as survived 20% of the time. And what we do is we plot, for a ROC curve, we plot true positive rate against false positive rate for different prediction thresholds. So I mentioned that by default, your logistic regression model is basically saying, and it's similar when you come onto the neural network, but it'd be a different structure. But here with the logistic regression, it's fitting a line, and then it's using that line to say, given this set of input data, then the output is a number between 0 and 1. The closer it is to 1, the more likely it's that they survived. The closer it is to 0, the more likely it is they died. And by default, the cutoff is 0.5. That's the threshold. So it says values that are greater than 0.5. It says, okay, they belong to class 1. They survived. Below 0.5, they belong to class 0. So we predict they died. But you can change that default. You can change that threshold. And in a lot of cases, you want to, because you may get better model performance by varying that threshold. Now, you don't just want to just randomly try different values, because there's a lot of values, there's a lot of different variables that you could chuck in. So you need to be a bit systematic about this. So a ROC curve will help you do this in a systematic way. So let's think about this in terms of a table, in terms of a matrix. So here we've got real world positive and real world negative. So the correct answer positive, correct answer negative. And we map that against predicted positive and predicted negative. So here, these are the cases that we say were positive, they survived, and they did survive. They are true positives. Here, we're saying these are cases where we predicted they survived, but they didn't in the real world. So they are false positives. We said it was positive and it wasn't. Similarly down here, these are cases where false negatives, where we predicted they wouldn't survive, but they did. And similarly here, these are cases, true negatives, where we predicted they wouldn't survive, and that's correct, they didn't survive. So we got this correct. So sensitivity is how good are we at finding the positives. So that's the percentage of correct positives out of all cases that were positive. So it's true positives divided by the true positives and the false negatives. So all the cases in the real world where they did survive, sensitivity is the number that I predicted that would survive out of all those that did survive in the real world. Specificity is how good are we at finding the negatives. So specificity is the true negatives, the number of ones where we said they wouldn't survive and we were correct, they didn't, out of all of those plus the ones where we said they wouldn't survive, sorry, that they did survive and they didn't. So out of all the people that actually didn't survive, how many did we pick up that they wouldn't survive? That's specificity. Now a ROC curve plots the inverse of the specificity, which is the false positive rate. So in other words, so specificity is how many, when I said something was, they wouldn't survive, and I was correct, out of all those that didn't survive. Whereas the false positive rate is how many did I say would survive out of all those that didn't survive. So it's, specificity is this out of that column, whereas false positive rate is this out of this column. And you can see that's the inverse of the specificity, because specificity is that over this column. So it's the inverse of that, just 1 minus that. So it plots the false positive rate on the x-axis against sensitivity on the y-axis. Sensitivity is easier to understand. It's just the true positive rate. How many times did I say, what's the percentage of times that I said they would survive out of all those that did survive? So you plot this for varying thresholds, prediction thresholds. So by default, it's 0.5, but we can have a threshold of anything between 0 and 1. So we plot all of those varying thresholds with their true positive rate against the false positive rate. And that creates a ROC curve. So this is a receiver operator characteristic curve. The bottom left, so we've got on the y-axis, we've got the true positive rate, that's sensitivity. And on the x-axis, the false positive rate, which is 1 minus the specificity. So in the bottom left, that's where true positive rate and false positive rate are both 0. In other words, that's where you've got your threshold set, so you never classify anything as positive. So in the Titanic example, you say nobody, you always say everybody died. You set your thresholds that everybody, you always predict that everybody died. That means you never pick up cases that are truly positive. So your true positive rate is 0, because you never pick up those that survived. But it also means you never say somebody survived when they didn't, because you're never saying anybody survives. So your false positive rate is also 0. So you never get any positives wrong, because you never say anything's positive. That's when your threshold is set, so that you just say everything is negative. Everybody dies. At the other extreme, at the top right, is where we do the opposite. That's where your true positive rate and your false positive rate are both 100%. So that happens when your threshold is set so that everything is classified as positive. You say everyone survives. So at the bottom left, you say everyone dies. The top right, you say everyone survives. That means that you pick up all of the true positives because you say everybody survives. So that means by default, you've got everything. You always pick up those that did survive because you just say everybody survives. But it also means that because you're saying everybody survives, all those that didn't, you get every single one of them wrong. So you have a false positive rate of 100%. You get all of them wrong because you're saying positive for everything. So down here, you're saying positive for nothing. Up here, you're saying positive for everything. So those are the two extremes of your threshold value. Everything in between represent your threshold values in between those two extremes, between saying everything is negative and everything is positive. So this allows us then to plot and show trade-offs between picking up more true positive cases, picking up more cases where people survive, but in doing so, also classifying more people erroneously as surviving when they didn't. Or to put it in non-Titanic terms, let's imagine you're trying to predict whether someone's got a particular condition. What trade-off are you willing to accept in order to say, well, this allows us to pick up more occasions when somebody has the condition, but in doing so, that means we tell more people they've got it when they haven't. So there's a trade-off, and depending on the context of what you're doing, it might be different. So we talked about, before that if you were looking at something like cancer, whether somebody has cancer, you might lean towards it's better to tell, although it's a horrible thing to tell someone they have cancer when they don't, is that better than telling someone they don't have cancer when they actually do and they're not getting them treated? So depending on the context of what you're trying to do, where your tolerance is determines that kind of trade-off decision. So here's the ROC curve. This blue dotted line that runs diagonally up here, that represents a worthless test. Okay. If you've got points along that line, it means the algorithm is no better at predicting a positive correctly than incorrectly. You may as well flip a coin. It's completely worthless. That means it's a really useful reference line, because if we're above that line, it means we're doing better than just randomly flipping a coin. So our model is doing something useful. Thresholds near the top left indicate points that are nearer optimal. In other words, they're very good at saying something is positive when it is, and they're rarely saying something is positive when it isn't. So they're very good at saying someone will survive when they do, and rarely saying someone will survive when they won't. Conversely, if you've got points near the bottom right, that indicates the opposite. That indicates that most of the time you're saying things are positive when they're not, and you're saying things are not positive when they are. Now, what that really means in practice is you've probably got your model the wrong way around, because it's clearly doing something. The worthless model runs along this line. It's doing nothing. You're flipping a coin. That model is adding nothing. If it's down here, it's doing something, but it seems to be doing it the wrong way around. That probably means you've just mucked up your code. So if you see a curve that comes up in this quadrant, you have a look very carefully at your data and your code. You're likely doing things the wrong way around. What you should see is a curve up here. And the bigger the curve and the more it stretches up to this top left corner, the better. So we can use a visual inspection of the ROC curve to try and give us an indication of how good our model is, how well it's performing. And remember, this is the potential of the model, because we're testing here, we're testing different threshold values. So we've got our the extreme threshold values of 0 and 1, but we're then testing everything in between, and that's resulting in different points on that curve. So it might be, so by default, it's 0.5. Wherever 0.5 lies on that line is the default. That may not be our current model performance, and we could use a ROC curve to say, actually, we could get better performance if we change that threshold. Because actually, it seems that if we get a better true positive rate, and we'd be willing to accept that level of false positive if we change the threshold to whatever. And in the workbook, the notebook that I'll link you to, it'll show you how you do that. How you can, you don't have to read it off by eye, although you'll look at that first, but you'll be able to say, okay, the best value seem to be around here. I'm willing to accept this as my trade-off. Give me threshold values around this point. So we can use our eyes to see, how good it is. If you've got a big curve stretching up to the top left, that indicates your model has a lot of potential. But we can also more precisely assess it using something known as the OROC, which is the area under the receiver operator curve. And we can calculate what that area is. So any area greater than 0.5, i.e. half this area, is better than random. That means we're above this line. So if you get 0.5 or something very close to 0.5, your model's rubbish. You may as well not. This isn't going to work. You're not gonna get anything from it because it's not able to do it. You might then want to look at maybe building a neural network to see if that helps, but you certainly aren't going to get it from a logistic regression. So if it's greater than 0.5, then it's better than random. So I should also say that these ROC curves are used regardless of your model. So these aren't just used for logistic regression. You also use them for all of the models that you do, including the neural networks that we'll see next week. So an area of 1, if you get that, celebrate, because that represents a perfect model. That indicates it has perfect sensitivity and specificity. In other words, it correctly picks up all of the positives and all the negatives. Well done. You might want to go back and check, because that's quite rare for that to happen. Just check what's happening there. But if you get that, that's astonishing. What you'll likely get is something in between, and hopefully something that reaches up into that top left corner, and this is better than this random classifier, flip of a coin. And as I say, we can use this ROC curve to determine what threshold we're going to use for our classifier, and we can determine the trade-off we're willing to accept, the percentage of false positives that we're willing to have in order to get a higher rate of true positives. Remember, true positives are good, false positives are bad. We want to be, when we say something's positive, we want to be right. So what percentage are we of false positives are we willing to get in order to get a better rate of our true positives? Okay, we'll stop there. Obviously, we haven't got time in 4 minutes for you to do these exercises, but I would suggest that you go off and have a look at this in your own time, particularly if you're going to be doing anything around machine learning. It's important that you understand these concepts. So in your workbooks, you'll see the number 3 notebook on k-fold validation, and the number 6 notebook, which looks at generating ROC curves, and both are pretty straightforward to do these things. So have a look at those in your own time. These are really important. There's lots of other stuff in there, but these are kind of fundamental to a lot of stuff that you will be doing in machine learning. And indeed, when we come onto the neural networks next week, we're going to have a look at ROC curves. So you might want to at least have a look at this. As I say, Mike's full resources are available at this link as well. So although you've got the older offline copy, which is got the some tweaks for HSMA for the stuff you've been looking at, for the full stuff, so I don't think I've made any tweaks to these two, so you might want to look at that in Mike's online materials instead. So we'll leave it there for today. As I say, next week we're going to look at neural networks in the morning. So we're going to talk about how neural networks can be used as a means of creating more complex models, something known as deep learning, and we'll show you how powerful these things can be, but also we lose something in terms of model explainability. But we do get a much more ability to play around with them and try and improve the performance. Then in the afternoon, we're going to have a look at synthetic data. So using techniques in order to try and create data that is completely made up, but is based on real data and is close enough to real data that it can be used in its place. And that's phenomenally useful for modeling, and also for, as we'll talk about next week, if you've got an underrepresented class and that's the class that you're interested in trying to predict, you can use synthetic data approaches to try and create more examples of that, because it may not be practical if you're trying to predict, from your GP data, patients that are about to get admitted within the next 7 days, and you haven't got enough of that data. You could use synthetic data to try and create new data based on the data you do have. And it can, we'll see examples next week of how you can create synthetic data for the Titanic data and use that instead of the real data to see how the model performance compares. Okay, we'll leave it there. So don't forget, if you haven't already, to upload to the GitHub as well. So have a look at the GitHub. We've got a few up there. If I refresh, yeah. Oh, blimey, we've got loads up there now. Fantastic. So if you haven't managed to finish that, do upload that. And it's great to see them all up there. That's fantastic. Have a look though at the 2 notebooks when you get a chance. Particularly, I'd have a look at ROC curves ahead of next week if you can. Don't worry if you don't get a chance before next week. We will go through stuff in the notebooks, but it might help you to at least have a glance over it in preparation. I'll also tomorrow I'll be posting up instructions for next week. You will need to install something called TensorFlow, which is Google's neural network structure. So you will need to do a pip install of that, and I'll explain how to do that. And you'll also need to install another library called ImbalanceLearn for the synthetic data session as well. So there's a couple of installs that you'll need to make ahead of next week's session, and TensorFlow can be quite large, so it might be worth making sure you do that ahead of time. Okay, we will stop there, pretty much right on time, I think. And any questions, say just post them in the Slack. But go back and have a look at this stuff in your own time, and see if you can get your head around it. But well done, you've managed to create your very first machine learning model. Next week, let's recreate the human brain and talk about neural networks. Brilliant. See you, everyone.
Bye.